So today we'll start talking about seam carving, which is a pretty neat idea. Very nice computer vision algorithm that's actually quite useful in practice too. And I'm going to just download a sample image and I'm going to show you the main idea. And then you should follow along this particular tutorial or lecture slides. But you can run it, you can try it out with your mega copy, and you can try it out on your own image. So what we're trying to do is, if we have an image like that, here this is one of the panoramas that I took. Then I can zoom this. Oh, here it is. Okay. But when I zoom it, then we lose quite a lot of detail. Like, it's much harder to recognize things. So what we want to do sometimes is to use an intelligent resize for images. So I'm going to try and look for another image. And I have never tried it with a cartoon, so let's try Tintin. Let's see, use that image. PD. Oh, maybe I should have just done it like that. %, and 50%, 70%. Okay, so you can see here's our original image, here's our scaled image. To 1/4, and very difficult to make out details there. So now what we would like to do is have a algorithm that does a smarter job zooming, because when you look at this picture here, then the sky part is not so interesting, right? And the mountains and the snow. Really, the most interesting part is the figure of Tanta and his dog Milu. So we would like to emphasize those parts and de-emphasize the sky and the mountains and the snow. Now, you should try this yourself. Try and find an image where the amount of detail varies greatly. So some other pictures where it works really well on would be images of ocean, beach, sand. These kind of images, because you want it to focus on the part with the waves. Maybe the clouds here, but then this sky part here should be eliminated, and the sand is also not so interesting. So you can try an image like that. Those work really well, or here, this kind of image. And I guess you can also look for Taiwan Ocean. See, yeah. So here are some pictures that you can use. I just want to give it a try with Tanta, even though I think I'm going to run into a problem because the figure is already the maximum. Oh, it's okay, actually, yes. We just scale it horizontally. So the big question then, of course, is how do we measure what does it mean to be interesting, right? How do we measure the amount of information that is associated with the pixel without understanding the image, without any semantic knowledge about the image? If you have a picture to find out what is interesting, you often need to understand what the picture is showing. So if you have a picture of some celebrity, then that person, unless you know this is a celebrity, you wouldn't know that this is the interesting part of the image, or something like that. So we need to have a automated system that we can use in order to figure out how important, how interesting a particular pixel is. And so one of the things we can do is we can measure how different that pixel is from its background and its neighbors. So a very simple way of describing what we mean by the energy of a pixel, the rough estimate of the information in a particular pixel, is how different it is from the background, the surrounding pixels. And that we can estimate using the magnitude of the gradient. So here we load the picture, and then let's just have a look at it. And here it is. It's a little bit slow, so maybe I just resize it to be it's already resized by a factor of 2. So I'll divide the original image by 3 just so that it runs a little bit faster. And doesn't use so much memory. So now we want to calculate the gradient. Now we can use the Sobel edge detector in order to run the gradient, or I can simply implement it from scratch, looking at neighbors to the top left, bottom left, below, bottom right, to the left, to the right, top left, top, and top right. Add the differences between those two, and then sum them up. Or a much smarter way to do it would be to calculate the gradient using the Sobel edge detector, for example. We could also use a Laplacian. Then you probably want to blur the image first. So here we have the original image. We read it, we resize it, and then we calculate the gradient. Now I'm going to normalize the gradient by taking the minimum and scaling it to 255. And then let's have a look at what that looks like. And so you can see we have very strong responses on the outline of Tintin, and nothing in the sky here, nothing in the back. And here, those rocks and the mountain edges are also considered to be interesting. So this is just running an edge detection on the image and showing the magnitude of the gradient. So now when I want to resize it, then I want to remove a continuous seam for a column or a row, which means one connected string of pixels. And if I want to remove the non-interesting parts of the scene, then the idea would be to take the pixels and use the ones that have the minimum energy, right? Because they are very much the same as the neighboring pixel. So if I remove it and throw it away, then that should be quite, that should not impact the image too much. And the problem with that approach is that the runtime complexity of this algorithm, we basically start out with a pixel. Then I can move to one of three neighbors, below to the left, below, and below to the right. Now I have three neighbors. Now I can three children. Now each one of those will have three children each, right? And each one of those will have again three children. So if the age is the height of the image, then the runtime complexity of the algorithm would be on the order of 3 to the power of age. And that would be way too expensive, right? This is astronomically large number. 3 to the, our image has 220 pixels or something like that. So 3 to the power of 200 is billions and billion times bigger than the number of atoms in the universe, which is about 2 to the 100. So this exponential complexity will never be able to search through the image from the top going down, trying to find the minimum energy scene. The reason for that is we can show the runtime of our algorithm for 3 to the power of h. So you can see that this is in billions. So until 10, everything is good, right? Our number is pretty small. It's actually too close to 0 to call. 15, things start to get bad. 17, it basically becomes a wall here. So there's no hope to possibly run this algorithm with anything like 200, right? 200 would be way over there on the chart, which means that we already would be much too high. Like it's just the vertical wall there. There's no way to overcome the computational complexity. Even if you build a computer that's 1,000,000 times faster, it won't have any impact on you being able to solve larger problems. Still, maybe you can go from 17 pixels to 18 by having a computer that's billions and billions and billions times faster, but it won't make any difference in your trying to achieve the goal of trying to go all the way up to 200. Now, the other reason why I like seam carving is it's not just the interesting computer vision algorithm and very useful, but it also is a very nice example of dynamic programming. And dynamic programming is an important problem-solving technique in computer science and engineering. It can greatly speed up some programs, and this is a very nice example of the use of dynamic programming. Oh, earthquake. Oh, okay. Do you have an earthquake in Taiwan too? In Taipei too? Oy. Okay, let me just open the door. This is a little bit too scary for me. Yes, okay. Then stay safe. Okay, good. I think that's it now. Oh no, now it's starting again. Okay, I opened the door. Okay. Anybody still out there? Okay, it is still shaking. This goes very long today. Usually it doesn't go so long. So here's a sample image that we generated, 5 by 10. I'm gonna make a table, and then let's say this is our image. And then we can run the algorithm. Assume that this data here is the gradient magnitude, right? So this is how strong the gradient is. -1 to 1. energy image. So it should just, that is T image. For P in path. Length T image minus 1. Yeah. Width minus 1, yeah. Why is that? So it didn't. Here. It should be length of T image 0 minus 1. Start point, yes. So now I can pick up a particular path. So we start at pixel 0, 0, then go 1 down, 1, 0, 2, 0, 3, 0, 4, 0. And I simply add up the gradient magnitude, right? So the 0 would have been this one, so 44, 25, 32, 57, and 4. And then we have other ones like 0, 9, 1, 9, 2, 9, 3, 8, 4, 7. Gives us an energy of 265. Another path 0, 7, 1, 7, 2, 6, 3, 6, 4, 5 gives us an energy of 209. So now the first idea you may have for implementing a solution to this particular problem is to implement a greedy algorithm. So that seems like a good idea, right? If you have three, you go down one row, then you have three possible children, three possible successors. So you can check which one of those has the minimum amount of energy and then just follow that one. Now that particular algorithm would run very fast. It's called a greedy algorithm because at each step you greedily choose your best looking alternative. However, by doing that, you may end up in a scenario where you search down the wrong path and there's no way for you to recover. Now, for this particular domain, so your algorithm may get trapped in a local minimum, and a local minimum is simply not good enough, especially because we can come up with an algorithm that can find the globally minimum path, a minimum energy path. And keep this particular project problem in mind. So we start here somewhere, right? One of these 10 pixels. And then we need to go down. So maybe 79, 25, 34, 88, 81. Then I get a the sum of those values as my energy. I want to find the minimum energy path. So here we have a greedy seam algorithm. So it's a greedy algorithm to do the seam carving. What we do is at the beginning, we go through the top and we find the pixel with the minimum energy. Then that's where we start. That will be our first pixel. And then we go through and we simply follow. We find the pixel below us that has minimizes the energy, and then that will be the next one in our path. Once we're done, we return our path. So just the first two steps of the algorithm on this particular image here: 44, 79, 96, 23. So 23 looks pretty good, right? Here's 22. So our minimum would be 22. So now I'm at 22. I have three possibilities: go to 30, go to 6, go to 25. In the greedy algorithm, I pick 6. Then 81, 13, 87. So I go to 13. Then 75, 23, 34. I get to 23. And then 2, 93, 56. So I end up with 2 here. And that is actually a pretty cheap path. So we may not be able to find, just by luck, we may have found the optimal path here. So here I get 0, 6, 1, 6, 2, 6, 3, 6, 4, 5. So that would be exactly this one. The one we found, right? 0, 1, 2, 3, 4, 5, 6 is here. Zero, 1, 2, 3, 4, 5, 6, 91. Oh, because we generate a new random path here. Oh, it's we're just starting from 1 to 10, columns 1 to 10. And then we can calculate the energy. So the energy here of that particular path would be 66. $22, $28, $38, $38, $41, $61, $64, $66. So it's this path, 1, 2, 3, 4, 5, that the algorithm found. That happens to be the optimal path, but that's just by luck. You can see that if, let's say here our gradient would be 102, then starting here already would give us a suboptimal path, right? Because then it would be the minimum energy we could get would be via the 56 here. So if I make this 56, then I would have an extra 54. So my energy would be 110 over the entire path. Then it would be better to do 23, 43, 17, 12, 25. But because I start here, I have no way to backtrack. using a greedy algorithm. I simply keep going always. So I'm not necessarily going to find the local optimum, the global optimum. I will find a local optimum. Now, the interesting consideration for dynamic programming is, first of all, let's do an introduction to dynamic programming. It's an optimization technique developed by Richard Bellman, and the basic premise of dynamic programming is that we break a problem down into subproblems we solve the subproblems we find and we remember, cache the solutions to the subproblems, and reuse those solutions in solving the larger problem. Now, because you're dealing with the subproblems, usually or very often dynamic programming is applied to recursive solution strategies. So you break the problem down into subproblems, apply dynamic programming, then you solve those problems using the same dynamic programming approach. It's been very useful in many different applications, not the least of which would be the table-based reinforcement learning algorithms, finding the shortest path in a network or in a graph is a dynamic programming problem that you can solve using Dijkstra's algorithm or what's the other algorithm? Floyd-Warshall. Yes, like Floyd-Warshall path planning algorithm or shortest path algorithm is an example of dynamic programming as well. So the two key components, however, are also that we can cache the solutions to subproblems. Somehow we can remember those. We can retrieve them. So that means we can store them, we can retrieve them, right? And then the solutions to these subproblems are useful in solving the original problem. And for the Levenstein distance, which allows you to measure how many editing operations you need in order to convert one string into another string. with some links if you want to have a look at it. And seam carving can benefit as well from this dynamic programming approach. So how does dynamic programming apply to seam carving? What are the subproblems? How do we store the solutions? And how do we retrieve them? Are crucially important questions that you need to answer if you want to apply dynamic programming to a particular problem. Now, one thing that is funny about dynamic programming, by the way, is that the name is really a silly name in the sense that it doesn't say much about the technique at all. Bellman, the one that invented the algorithm and the name for it, basically said that he had to apply for research grants, and there was a lot of optimization research going on at the moment, so he didn't want to have another optimization algorithm or optimization in the title. But at that time, I guess computers became popular, and so programming was a hot term. And also, he thought dynamic is a good name because who does not like something dynamic, right? Dynamic is always good. So he basically picked dynamic programming, not because it's particularly well represented the technique or explained the technique, but just because he thought it was a good name to get research funding. So think about this for a second. Back to our original problem. We want to find the connected path that has the minimum energy for a particular cell. Let's say this cell here. I want to find out what the minimum energy path is. How can I do that? Or how is this supposed to work? Now, the complexity that we were considering, 3 to the power of h, that is looking at this problem as a tree structure, which means that there's no cycles. Each path is completely independent. But you can see that this cell here, there will be 3 paths that will try this particular cell, right? From here, we may go to the right. From here, we may go down. And from here, we may go to the left. So what I can, the path, then, the problem then can be rephrased as saying from this cell, recursively find the shortest path that goes through these three cells. And that's exactly what we're doing with our seam carving algorithm. And the point is, the reason, so if there were really three different cells, then caching would not be possible, because I run out of memory very, very quickly if I have to generate three entries every time I test a pixel, right? Then this would also grow with the power of 3 to the power of h. So that would not be feasible. However, for each pixel here, once I know the minimum path, let's go to the top, right? For this 50. Once I know that the best path for me to go, the minimum path for me to go to the top is via this one here, 23, then I can just remember this. And all the other paths, this one here, doesn't really matter. So the only thing that really matters is for each cell to remember, to calculate and remember what is the cheapest way for me to go to the top. Right? So that means we need to keep adding, we need to sum up the values for each pixel, not just its own value, but all the way to the top. So for this pixel here, I want to check and I want to remember the value that I, from here to anywhere on the top row. In this case, that will be 22 plus 6 plus 13, right? Now, these are the, so if I know 35, 41, if I know 41 for this pixel, then I don't need to worry about the other neighbors that give me a larger, a higher ranking, because I'm only interested in the path that will result in the minimum cost. So I can throw away all the other paths, which means that for each pixel, we really only need to remember one path, and that is the path to the top with the minimum amount of energy. So here, when we look at it from a figure, for every pixel, if I go backwards, I only need to remember which one is the one with the minimum amount of energy, right? But now I don't want to just add up from this particular pixel, the cumulative sum all the way up to the top. Another way of thinking about this is, if I'm on the minimum path, then the minimum path will go through me and through this pixel, never through this one, never through this one. So the minimum energy of the path at this point here will be the minimum energy of myself, the energy of myself plus the minimum energy of the path all the way to the top. So the minimum energy path through that pixel will be the gradient of the pixel, the gradient magnitude of that pixel, plus the minimum of the path to the top neighbors. And then we can implement. So what we need to remember is we need to have one block of memory for every pixel. Right? So if it's a 1,000 by 1,000 image, I need a 1,000 by 1,000 array. That allows me to store the cost along the path from the top to this particular pixel. So here's the code for finding the minimum energy seen. So we generate an array carve, same size as our image. And the first row is exactly the row of the gradient magnitude of the image. Then we go through, for each one of the rows, we look at the neighbors. We select the neighbors if they exist and calculate which one of those gives us the minimum energy. Then I can remember that minimum energy point here and update this part recursively, iteratively here in a loop. So maybe we can highlight that a little bit. Let me try and make that as an animation. Array 0. For y in range height. And I'm going to flip the y-axis. For height. So ax.text. x would be x times c width one c width length height multiplied by c height minus length height minus y multiplied by c height to f dot format array y x Okay, let's try that. If array y x is not none. Okay, I said ax star. comma, C height times C height. The width .510, yeah, will come. Plus 5 multiplied by C height, and here text. How can I make the thing larger? Ah, it's the wrong axis. Now we have the size, except it's a little bit too big, so I want to make the font smaller. Much smaller. Still too big. Okay, then we change the size of the cells. To Okay, this needs to be twice as big. I need to add one more. Plus one. And then let's see. Okay, so that gives our coordinates. Make that equal sized. Okay, now it looks better. Now we can also draw the lines. For y in range height. So a is equal to ax dot plot. From 0 to from 0 to c width plus 1. And I need to draw two more, so I want to go height plus 1. And the y coordinate would be y multiplied by c height. And the solid line line width 2. See what that looks like. Draw array AX plot 0 width. Oh yeah. So here we draw the horizontal lines. Don't think I need to do that anymore. Oh. Black, I think, is K. Okay. And then we plot the vertical lines. So this will start at x times c width. X times c width. And the y coordinate would be from 0 to y times height times c height plus 1 c height. Okay, 1, 2, 3, 4, 5. Yeah. I think it'll be just like that. Okay, now we need to set our array there, and okay. Get rid of the ticks. Okay, and set the limit to be correct. So this, okay, we can see I can make it a little bit bigger and also bigger font. What does it actually do there? These are scaled by the transform 6. All right, and now the carving. I can also make that a numpy array instead of this. Also, if it's a negative number, I just don't draw it. Timage.shape. Multiplied by -1. And that I draw AX2. So here we start out, we have image with the gradient magnitude. Initially our dynamic programming cache, our carve, is empty. And then we set it first so that with the top row here, so let me see how I can do this. Frame. Carve is equal to T image So we draw this and we draw the curve. Okay. Then we set that. Let me try if that works. Ah, zero, 1. Okay, so we start like this, then we copy it across. But oh, let's change that. So if that's greater than 0, if previous is not none, and previous yx not equal to array yx, then color is equal to red, else color is equal to black, and draw the text in color. Hmm. C for C in row, for R in car. C in R. Color, yeah. Color red. Oh, again. Oh, I don't pass it in, that's why. Silly. Okay, then let's change that to 3. And I think this is overkill. I think I can just do this. No, maybe not. Lists are passed by reference in Python, so sometimes you have to make sure that if you update things, you either create a new one or make a deep copy. So now it shows that which values have changed. Step is equal to 1. Two plus the width. So 2 plus the width. Oh, how come? Hello? Can you hear me? I can. Okay. Okay, good. Okay, so then carve. So now I'm going to do the first row. Carve 1 x is equal to for tx in -1, 2, 1. So -1, 0, 1, and we iterate through that. Mu x is equal to x plus tx. Minimum is equal to none. If the minimum is none or the carve y minus 1 if nx greater than or equal to 0 and nx less than width. The minimum is 1. Y is equal to 1. Y minus 1 nx less than min. Min is equal to that one. And then we iterate through. Now we know the minimum. So this will be replaced with carve with image t image yx plus minimum. Okay, let's see if that works. So first we copy the first row and then we update our values. So that looks pretty cool, except why is this 104? Should be this one 44 plus 25. 44 plus 25 is 69, not 104. 79, here we get 25 plus 44, 79, 96. Or carve y minus 1 nx yx minus 1, 0, 1, and then 2 it will not run. Ah! This should be range here. That's 69 now, 69. Well, we got 25, 68, 66, 73, 52, 28. Okay, that looks pretty nice. And now I change my draw. Plus 0.2, 0.15 maybe. And I now can do the entire thing and no print red. So y would be step minus 2 divided by width. And that means I can run more here. 5 times 10 is 50. So let's run 50. So this is the step. X is equal to step minus 2 modulo width. So fill in the first row. But my offset is wrong, yes. It's this plus 1. It's this plus 1. Okay. Yes. Plus width times height. Index is out of bounds. Wouldn't be height minus 1 here. Would be height minus 1 here. Wouldn't be height. So 32 plus 69, yeah, 101. So I like this pretty cool animation, I think, of the seam carving algorithm. Right? And now, as you can see, what is the minimum path through the image? How can we find the minimum path? After I fill in my dynamic programming cache, how do I find the minimum path? How do we find it? And what does each cell entry now in my dynamic programming cache, what do the numbers actually mean? Once you figure that out, it'll be easy to find the minimum path. The minimum energy path. Think about that for a second. And by the way, here's exactly the same program, the same algorithm, checking for the gradients and updating our carve table. And this would be the output for the image from Tantan. So this is considered to be a lot of energy there. Very strong response, these parts here. And the other ones are hard to see. So then we implement a routine to find the path. So let us check here. Find the minimum path. And then plus height. Dot plot frame.extend. Point 4. Let's try that. And this should be step minus this, so this will be from 0 to loop. Okay, and this one should be 17. Any2. Okay, so let's see. Fill in our dynamic programming cache. And it's a cache because whenever I answer these, fill in these pixels, I need to look up the value of the pixels above, right? So I reuse the values here over and over again. Or I reuse the values several times. Oh, maybe the coordinate will be off. No. Hmm. See what we have here. Oh, this is too big. Min pass. I think we're plotting the wrong thing here. Two hundred 1961. Oh, carve. Okay, let's see what we have here now. Now let's check. Hmm. Loop 80, 81, 82, 83, 84. -2 minus 2. What's this? Okay. Print 0 loop. X. Oh, I think it's Y and X. Yep. Yeah, we can jump ahead. Green. Oh, doesn't draw anything. Has 1, 2, 3, 4. And 5. Yeah. So why doesn't this plot the path? This would be the x coordinates. From 0 to loop, this would be the y coordinates. Color is green. Ugh. Silly. Zero 1 0 0.5. What happened? Make it green. And this. I don't know where it plots the arrows now. I think these coordinates are off. I think they're only in the first quadrant. Ah. I may have to multiply by c width. Oh, I don't have the C height. Yeah, okay, never mind. That'll be a little bit too difficult to fix now. Just to get the arrows, but what each cell tells us is from the top, what is the cost of the minimum energy seen to that particular pixel. So if I now want to find out what the minimum energy seam seam is, then I need to look at the bottom row, and then here 66 is my minimum, right? So that means that this pixel will be on the minimum energy seam, and then all I have to do is look up. Then I need to go back from the bottom towards the top, look up and find the one that minimizes my energy. So now from 66, here's my next element in the path. So we'll go from here to there, to there, to there, and then this is the minimum energy seam. Then I can remove all of these pixels. I can delete them. In that case, I will have reduced the size, the width of the image by 1. Right? Now, if you want to zoom only the width, you can do that, or you can rotate the image and then run the same algorithm. Then you end up with an image that is reduced in width and height by 1 row and 1 column. And then you can do this iteratively, repeatedly, in order to then reduce the image more, like 10 pixels, 50%, something like that. Now, one thing that would be nice to do would be if we would be able to remove multiple rows or columns, but that doesn't work because we may remove pixels that are actually belongs to 2 paths that we're both trying to remove. And in that case, there's only 1 pixel that we can remove. So here's the same thing again for a path. For this particular image, it starts 4, 5, 0, 1, 2, 3, 4, 2, 3, 4, 5. So it starts here at 25. From here, it'll go to 36, 19, 28, and then 22. 4, 5. So this is the image. So here now I can plot it in the image, and I can plot both the greedy path, which is the non-optimal path, and the optimal path, the min path. Then for my data, it should look like this. The greedy path would be here on the left edge, and the blue path is the minimum energy path through the image here. Now I need to swap the thing when I draw them. So he has red pants in the original image. Yeah, okay. But this one is correct. our image, and then yeah, so I just had to swap the color channels. So the green pass is the greedy algorithm. The blue one is the actual minimum energy seam. And then the only thing left to do is to remove those pixels that are on the path. And then we can see how much our image now changed. So now we're removed one column. So we have one less. And then I can implement that in a loop. So we start with our original image. Then divide it by 3. Actually divide it by 2, we try. And then let's remove 100 pixels in the vertical. So we carve a seam, number of iterations. Here we're reducing, we're deleting one row at a time, one column at a time. Now again, it's computationally expensive because even though we would like to, it's not possible to remove more than one seam because they may overlap unless you can guarantee that they're not joining a single pixel. Not much you can really do in this case. And then here's our zoomed image. And it's pretty good in the sense that it kept a lot of the shape of Milo, except I want to, wait, I need to swap the color channels. And now let's just see 0, 100 by 200. So here's the original image. And here is the output of the computer vision, the OpenCV resize operation, the third one. So why is ours smaller? So how many so height? How come it resizes it so strangely? Should be height, width. New height, new width is height divided by 2, width divided by 2. So we start with 6. Wow. 662, 1280. Then new height, new width is height over 2, width over 2. Resize the image to new height, new width, or new width, new height. 780, 540. So it should be resize, should be new width, new height. Width and height, yes. Okay. Okay. And here's the result. As you can see, in our smart seam carving algorithm, nothing much really changed here. We removed parts of the image. Here are the images resized. So the left one is the original image, and then the seam carving one. So here we removed 100 pixels, here we removed 500 pixels. So you can see that for the Tantan, it's a lot thinner now, right? Whereas here, most of it survived. None of it was actually cut off. Also the mountain, the dog, all are not squished in. So let's do this again and run it a little bit longer for 200 to scale it a bit more and make it a bit more obvious. So reducing it by a factor of almost almost 1/3, from 640 to 440. So we're halfway done. Okay, and now we can have a look. So now we scaled it down a lot more, but the Tintin still looks reasonably good, right? A little bit thinner maybe, a little bit less, lost some weight, much less so than the unprovoked or the dumb zooming, right? Also, the mountain still exists, is not scaled down. The dog, even better. And the footprints have not been removed. Right? So most of the parts that were squished out were really the sky and the snow areas here. If you can see, like those rocks move further to the left because quite a bit was removed here. You can visually see that the rocks, the start of the rocks and the footprints are further to the left here. So they weren't scaled down so much. Also here, that mountain has been scaled down. It looks a lot more realistic or a lot closer to the original in uh, the seam carved image. So I really like the seam carving algorithm, for the smart zoom that you can do with it, which is a pretty neat effect, but also because it's a very nice example of using dynamic programming. Now you can do some more interesting things with it. So for example, if you have a picture of your old boyfriend or girlfriend and you don't want them in the picture anymore and you want to remove them, then that's actually possible because you could highlight in the gradient image, in the gradient magnitude, you could just say that these pixels here should have 0 energy, and then the algorithm will take them out, will remove them, right? Because you can't get any better than 0 energy as far as your stream is concerned. So you can even control it. Like there are programs you can get and apps for your iPhone and your Android phone where you can draw you can draw which parts you want to keep, which parts you want to remove. That is often done using seam carving algorithm. Okay, then that's it for today. Actually, let me run the whole thing and then finalize it. Okay, so we're just going to run it for a while. But that's it. That's the end of the class. Today I will just upload the lecture slides then.